Welcome everyone to yet another live stream. Some quick update here, findings on Twitter. Robert Graham, provocateur here, writes, so Apple simply cheated. They added Intel's memory ordering to their CPUs. And so what he means is the usual black magic, otherwise skeptical. Black magic, yeah, you had me at black magic in previous stuff. Not amused, but so he's talking about the ARM Intel emulation, which of course benchmark have found M1, of course, performance on the level of latest AMD Zen, my previous video, and the Rosetta 2 emulation that I think is partially LLVM based with open source project and all the many previous videos, has pretty good performance. And he writes here the biggest hurdle with memory ordering is the ordering which CPU sees modifications in memory by each other. It's the biggest problem allegedly. So I'm actually not really sure if he has inside knowledge. Maybe I should have checked his created backup. Yeah, something doing not really sure. So not really sure. This could always be hearsay, could be speculation, but it could make sense. So what they mean is, so he says memory ordering is expensive, and we see this maybe not necessarily that, but that QEMU. So basically, this Windows x86 emulation on ARM and Apple's Rosetta, similar to the Rosetta 1 from previous PowerPC transition. And so internally that uses the same technology as QEMU, what we usually run here on Spark and stuff. I don't know, have this in history. Of course I have somewhere like here, obviously. And personally I find this quick emulation performance a little bit lagging, but hey, at least we have nearly any architecture, and other people donated 10,000 of their work hours for free, so I'm not complaining about that. But certainly QEMU emulation performance is a little bit lacking and leaves a bit to be desired. So much is, as much as I certainly appreciate, and using QEMU for 15 years already, certainly one of the earliest users there with Rock Linux NT2 already in 2005, 4 and 3 and stuff. The more I am impressed with the performance that Apple and even Microsoft, people of course complaining Microsoft performance garbage, I have to say the Microsoft x86 on ARM performance is probably honestly still better, so much to reality check and being honest with ourselves, than QEMU. And the more I'm impressed with Rosetta, as with all the hashtag peak bugs and criticism of Apple's vendor login and not upgradable SSDs and memories, the more I can also appreciate when they do good things, and once in a million times they do. So I also wouldn't call it, so he writes, simply cheated. I wouldn't call this cheating. So what he means is with some complex details, meaning memory ordering, we had these previous videos of myself here, various instruction set architectures from x86, Spark, ARM, MIPS, RISC-V. And what they mean is that all the processors, go away with this donation, you have too many millions anyway. Memory ordering is that all the processors since the Pentium Pro, I guess, and SGI, was it T2, R10K, doing speculative execution. And with speculative execution, because previously processors were in order, so one instruction like load, store, multiply, add, they were all executed in order, meaning what the code did in assembly code, as in this pseudocode here, so that you would get A plus B plus C, store in sum, and then call print with this argument register. And so in order is of course trivial. You have one instruction after the other, and there are no surprises. However, with out of order and speculative execution, since the Pentium Pro, the MIPS R10K and similar such processors, you of course have the issue that the processor has potentially dozens, if not nowadays allegedly maybe hundreds of processors in out of order execution buffers. And then of course you have plenty of load and stores that can occur in some order, and all the processors have some different order, whatever the processor implementers saw fit. Here's some Wikipedia table that you probably need to take with some grain of salt. So the whole thing is actually rather complex, and the topic of a dedicated video, maybe sometime soon, which you probably want to share, like, and subscribe. So loads can be reordered after load. So meaning you have in your program, you write here high-level code in C or higher level C++, Rust, and machine code is generated. You have the several, like a matrix multiplication, or in 3D data, any other such thing. You have dozens, if not hundreds, of loads. Can the loads be reordered? Because your hardware may see this, your NVIDIA card may see the loads, or other. Also with caches, cache synchronization with multiple processors. So loads can be reordered after stores. Stores can be reordered after stores. And you see on ARM or Alpha and ARM, and yeah, MIPS is like MIPS, depends on the implementation, YOLO, whatever, reads a freaking manual. But so basically on Alpha, ARM, they are relatively relaxed. A lot of things can be reordered. And of course, there are memory barrier synchronization instructions on all the architectures. So if you have memory, like volatile code of operations that you need to make sure the hardware gets in a certain order, or like the hardware gets and then there is some doorbell register of 3D API, hammer in there all the registers, or SCSI fiber channel QLA, QLogic controller, previous video. Usually you have a couple of registers, IDE, SCSI, and graphic and not. You write all the registers and then memory barrier, and then finally write some doorbell thing of we are done programming, do the work. And with this kind of stuff, it's of course important that the hardware or other processes see, especially stores. So stores can be reordered after stores, and you see x86, not so much. And he says, I've not personally implemented this yet, maybe soon here on this channel. We started some JIT already, but he says, to be taken with some grain of salt, this could potentially be a large headache. And so what he says, Apple simply cheated. I wouldn't call this cheating so much to hear people always fighting over their wording on Twitter and stuff. Honestly, with all my criticism on Apple, I don't call this cheating, I call this clever engineering. So Apple allegedly, maybe according to those rumors, have innovated for once. As ARM is not an invention of the Apple Silicon, not an invention that Apple obviously licensed the instruction set architecture from ARM. So maybe they have some model-specific register thing to toggle memory ordering, so that, because, so how does it work? Here's some nice teardown at some BlackBerry block of Windows 10 on ARM. So how does this actually work? They have here some tiny example. You also see the similar on QEMU. So some extremely short x86 code, push, EBP, the extended base pointer, move, ESP, stack pointer, pop, EBP, knob and jump, not even sure, probably some whatever garbage. Anyway, so this translates the CISC complex instructions, allegedly, according to, I hope he got this here from some fine attaching a debugger or such sort. So store here, move, so push, move, this load, pop, EB here, so add here something of whatever, get, jump, function address, and then branch. And so this is all the code, and this looks relatively straightforward, is somewhat one-to-one mapping. The mapping, so this is actually relatively cumbersome function pro and epilogue code here. That is, a logic code will be much more directly translatable of add, although CISC of load and stores in all the instructions, but otherwise relatively directly translatable, as I said in some previous videos. So if you have some add and div and multiply and stuff, you just need to take care of loading some values, like with this inline memory load and stores of move of this x86 instructions. You would factor this out, so you would have from one instruction 2 or 3 to mimic this, but otherwise it's a relatively straightforward mapping. And it should be relatively fast. So he also has here some other more details that are not necessarily as interesting, but and caches and whatnot. But just that you see also people ask, so I also wanted to show you that so this Windows stuff, because some people on some, even our Discord channel or other websites, like it's some hardware, it's some software, it's like whatever. So it's like QEMU, it's software, not virtualization. Virtualization usually means running this directly in hardware with maybe some special hardware virtualization mode to compensate for some otherwise not directly para-virtualizable hardware quirks. But emulation is the difference of translating this on the fly one instruction set architecture to another. And so this would be some load and stores. And as you see, so just mapping this one-to-one can lead to different memory ordering. And this could make things probably quite slower. So that would make some sense. I don't have any additional research into that. I also wonder whether the DTK here that we have, the developer transition kit, has already in the 812 set the same memory mode, or whether the M1 is significantly faster in Rosetta 2. I don't know. So I would imagine if this is true, it could be some model-specific register thing where you can toggle some bit of like high-performance ARM stuff, or of course this is not doing more, right? People always think like Linus Tech Tips also misspoke, in my opinion, in yesterday's or 2 days ago video where they called out Rosetta 2 performance and they said something. They had their graphic, and maybe they even had the same post here, and they had here a graphic of directly executing, like it looked on their graphic like the x86 stuff would like go directly through the CPU. I find this highly unlikely because, as seen in previous videos, the high performance Apple only gets with a very wide instruction decoder and instruction issues. So if they would decode x86 as variable length instruction set stuff, it would add significant burden on the CPU instruction decoding and issuing there. So I don't think that it makes much more sense that you keep the hardware as high performant and less complex and unencumbered as possible and do this in software. And in my opinion, if this is true, again, only speculation, it makes somewhat sense. Could be model-specific register to turn on x86 ordering, meaning certainly degrading performance a little bit of more ordered load and stores and simply not out of order load and stores as much as otherwise possible on ARM, and do this strictly for x86 to only allow stores can be reordered after loads and incoherent instruction cache pipeline whatsoever. Anyway, and all the other stuff not. So it makes somewhat sense, and could also be, if true, it could be an competitive advantage over competitive ARM processors on Windows for the foreseeable future, unlike other people at Qualcomm and stuff copy this invention. I wonder if we will see a patent publication of this. This is also why personally I wish the death to software patents, because if Apple patents, again, this is something that processors do differently, but Silicon Valley companies, bets taken on what are the chances that Apple patented changing the memory order of some one non-native format to another. But anyway, mostly wanted to share this, among other things also here in how does this work look allegedly to other bloggers. I hope this is accurate, because I don't have an ARM Windows machine either, because sustainability and stuff and minimalism and have already enough stuff, and I don't need stuff that I don't need. Last but not least, of course, people also said at times this is done in hardware. No, it's not done in hardware, and this is of course pure software on the Windows side, and for the most part accepts this memory ordering on the Mac side. And 64-bit is coming, 64-bit x86 emulation to ARM on Windows. Not really sure why they have not done this from the start, because personally they also wonder, I personally always wonder how the big companies there like Microsoft, Google and Apple always need so much time to do this stuff, because given the higher performance nature of 64-bit, I would have done this earlier, like at the product launch, because it certainly boosts the performance quite a bit, especially as there are much more general purpose registers, 16 instead of kind of 8, not really 8, but nearly 8, and 8 to 16 more or less, give or take, minus a couple of ones. And the only thing might be like single instruction multiple data. That certainly is also not fun to translate from x86 single instruction multiple data to certainly vastly different and incompatible on the ARM side. So yeah, but maybe as single instruction multiple data is an issue, but otherwise, of course, this will give a quite nice speed bump here on the Windows side as well. I only wanted to share this to give you some more information and background information and video I can point to. So nothing of this most likely has special hardware support, except the memory ordering, and on both sides it's pure software. For birthrights, Apple M1 x86 memory model into Bing, and this live stream was the first page. I'm already a subscriber, so it took me big sense. Not a big single. That is amazing. Welcome and happy to hear that. But yeah, this other kind of stuff, I hope you appreciate this. It's still not the biggest channel yet working on that, but it's still a hobby, so trying to share you some insight on a daily after work and lunch break basis. I hope you learned something, and otherwise I will also continue with the low-level code operating system and just in compiler. So if you want to see that in action, I've already done some early enablement and JIT code for the most popular platforms. So this will be also coming next. And yeah, interesting stuff. But of course, both are only bridge solutions. Of course, you don't necessarily want to run either of them. As more impressive it is that on Apple's implementation, it's so performant that given the high performance M1 ARM silicon, users are actually pretty happy with just running this in emulation. And of course, in the long term, on the other hand, it's of course that giving all this engineering efforts and resources being deleted in a couple of years after some transition time, probably in maybe 5 years. On the PowerPC side, I think it was 10.6, maybe the last version. I think Rosetta 1 deleted in 10.7. In my opinion, always a little bit sad to see if companies have the solution. Although actually Rosetta 1 was licensed from a company that IBM later purchased. So maybe it was cutting costs, but this time it's developed. Maybe this time it stays longer, who knows. PowerPC Rosetta was company that was licensed from later it was purchased by IBM. Quick Transit, yeah, I think so. This was Quick Transit. Many people don't know this always. Apple always gets credit. I think this time they have done this themselves, mostly based on LVM and or their, maybe they could probably leverage quite some JavaScript code they already had. But yeah, this was Quick Transit, cross-platform virtualization from Transitive Corporation, later purchased by IBM. And also, what many people didn't know, that it was also not only extension of the Dynamite technology developed at the University of Manchester Parallel Architectures and Languages Research Group, but also offered by Silicon Graphics, used Quick Transit on their Prism visualization systems and based on Titanium 2 on Linux, and of course, most prominently, Apple for Rosetta, and later IBM announced partnership and eventually acquired them in 2009. Never heard about this again. This is a fun technology in IBM's attic there. Anyway, that's it for this video. I hope you learned something, whether it is details how this processors do memory ordering and that they all differ there internally. And last but not least, of course, this stuff similar to QEMU. If you want to see this in open source, you can look into QEMU, how it's implemented there. And otherwise, I hope you learned something, and always take these rumors with a grain of salt, and I hope to see you soon for the next videos and live streams to come.